Greetings, people who watch math videos. I have behind me the binomial theorem, and today we're going to prove it by induction. You may recall that the process of proof by induction involves two steps. Here we have the base step where we choose n equals 0 and we demonstrate the theorem using that value. First of all, we grind through the tedious calculation of x plus y all to the power of 0, and we get 1. Okay, now let's see if our theorem works. And so now we use the easy theorem, which in this case takes more steps. And we grind that through 0, choose 0, all multiplied by x to the power of 0 minus 0 times y to the power of 0. And all that works together. If you want to check that with your calculator, it adds to 1. Okay, so the base step has been demonstrated that the theorem is valid for that one value, n equals 0. And now we move on to the meat of the proof, the inductive step. Here we have our inductive step. Now for the inductive step, we're going to assume that we have found some integer p for which this theorem holds. So what we're assuming is that x plus y all to the power of p equals all this stuff. And this is really, it's the same as the statement of the theorem that we've already given, except where we had n before, we have p. So the structure is entirely the same. We're just replacing n with p. So we're saying, what if this theorem was true for some power that we will call p? And then we're going to take that and we're going to run with it. And our goal is to show that that assumption implies that the theorem will also then be true for the number following p. Okay, so you'll see here that where we had p up here, up at the top, we've replaced everything with p plus 1. Okay, so we're following our assumption to the logical conclusion. We're saying if this theorem is true for some integer, which we'll call p, then it has to be true. It has to be true for the integer that's one more than p. Okay, so the next step, the next part of this step then is to expand all of this material algebraically. Suppose we wanted to generate the p plus 1th power of this binomial x plus y. And suppose also that we've already multiplied out somehow we've obtained this polynomial x plus y to the power of p. Well, then what we could do is multiply by x plus y. Okay, just as if, say we wanted x plus y all cubed. Say we wanted the cubic. That would multiply it by the quadratic. We'd multiply it by x plus y squared. Okay, we'd have that expanded out, and then what we would do is then we would distribute the x and the y separately. So this is what we're doing here, and I've named each of these bits A and B so we can keep them separate and keep a handle on them. So what I've done here is I've got x, and I'm going to multiply that by x plus y all to the power of p. And I've got y. I'm going to do the same thing with y, and then we're going to add everything together. Okay. So this is my a portion right here. This is this bit. Okay. So there's my x, and I'm multiplying it by my expression for x plus y to the power of p, because everything from the sigma and beyond, that's our expression that we are using for x plus y all to the power of p. Okay. Now, when I multiply each term by this x, as we have over here, then we're going to have the exact same polynomial, except x will be incremented by 1 because we've multiplied each term by x. So this on the right is identical to this on the left, except we've added 1 to the x exponent. Okay, and then now we're going to do the same. Section B, we do the same with y. So here's this is the same expansion, or not expansion, this is the same formula for x plus y all to the power of p, but now we're adding y to it. I'm sorry, multiplying it by y. So when we do that, we bring y into the expression, and now we increment the value of y by 1. So now instead of y to the power of k, it's always 1 more than that. And now the x exponent has stayed the same. So in section A, when we multiply the polynomial by x, we increment the x exponent by 1. In section B, when we multiply the polynomial by y, we increment the y exponent by 1. We're going to do some things to parts A and parts B separately. Now, I realize this is all starting to look a little bit hairy because we've got all of these summations, and they differ only slightly from each other. So I can see how it's going to start to, if it hasn't already, swim around in your head. So I get that. Once we're done with the formal proof, we're going to take a look at an example of this whole mechanism using a specific polynomial. All right. And I think that will help us solidify what's going on in these steps, so that you can really feel it down in your liver. So let's start with A. We've got k equals 0 to p, which means we've got p plus 1 terms. Okay? And we've got the same thing exactly down here in B. We've also got p plus 1 terms. Okay, so let's maybe treat this like a column. There's p plus 1 terms. Okay, now we've also got the exponents. They add to p plus 1 because we got p plus 1 minus k plus k. So we have the exponent total is p plus 1. P plus 1 exponent total tot. Right? And again, I mean, it's all part of the same. We've got the same thing here, or the exponents add up to the same. P minus k plus k plus 1. That also adds up to p plus 1 exponents. Okay, so similarities here, the exponents are divvied up differently. Okay, but now here's what we're going to do with A. We're going to remove the first term. Okay, we're just going to keep it out. We'll add it all together, so we have an equality. But this term right here, I mean, that's the term that we'd end up with when k equals 0. Because when k equals 0, we'd have p choose k, which is p choose 0, and that's what we have here. Okay? And then minus k would be 0 minus 0. So we'd have x to the p plus 1, and then y to the k. So we really, we'd even have here y to the 0. We can put that in there. And now everything else here is the same, okay, except we have to make sure that we start our index a little later because we removed that first term and we've set it off on its own here. So now instead of going from 0 to p, we're going from 1 to p, which means that we're going to have p terms here, p terms. And there's one term here. Okay? So our total terms is still p plus 1, and our total exponent here is still p plus 1. Exponents are unchanged here, p plus 1 exponents. Okay. Now down here, what we've done is we've removed the final term. Okay. So what does that do to the b expression? Okay. Well, all the stuff in the middle, all that remains unchanged, and we're still going from k equals 0, but we stop before we get to p. So we're only going to the p minus 1th term. Okay, so this is all the same as we had before, but it's only the first p terms. Okay, it's the first p terms. These were the last p terms. Okay, and then it's the here's one term right here. Okay, so our total is still p plus 1 terms, and the exponents, they all add up to the same thing. But what we've done is we've taken a bite out of each equation. Here we've taken a bite out of the beginning of the equation and set it aside as its own term. And here we've taken a bite out of the end of the equation and left its term over here. Okay, so now what we've got here is before, when we separated these, we could just simply add these sums back because this k equals 0 to p, k equals 0 to p. Everything's the same. We could add them back and figure out something to do with this, but we could make it all one. All right. But now here it seems like we're going a little bit further away, because now we've got here we've got k equals 0 to p minus 1 and k equals 1 to p. How are we going to get these sums back together? Well, this is why we're going to do an adjustment to the index here. We still have p terms, okay, in the summation. But instead of going from 0 to p minus 1, we're going to count from 1 to p. Still p terms, okay? But now we really just changed what our index is, okay? So that means that p is just a number. P is constant throughout this whole adventure, okay? But k is the thing that changes. So now up here, we want our first term to have k equals 0. But now we've got k minus 1, so that because k is starting with 1, k will still equal 0, okay? And then our final term will be p, okay, or sorry, k will be p, okay? So it'll be p minus 1 here, whereas k was already going to p minus 1 up at the top. So the point is that these amounts here will all evaluate to the same. We've just changed what we've called the indexes, right? Okay, so this is all the same over here as well. Okay, moving on. I've created a visual of what we've done just now with A and B. So this bit in between where these rectangles overlap, those are our summations. And so you'll see what we've done is we've essentially, the whole point of this was to be able to slide A and B over with respect to each other so that we can add like terms. You see, we've got like terms here. So we want to be able to add these all along, okay? Now, what differs in these is the coefficient, but we can live with that. We can just sum them up right here. And we've got a nice handy dandy rule, which we talked about previously, okay, Pascal's rule, which allows us to sum these binomial coefficients to p plus 1 choose k. So, which is exactly what we've done. Okay, we've summed it to p plus 1 choose k, and now everything here stays the same. We've got p plus 1 terms. We're going from 1 to p. We're almost done, except now we've got these rogue terms which I keep carrying down. What will we do with them? What have we wrought? We're wanting to combine all of these elements into one formula that looks remarkably like this. I mean, we're almost there, except we're only going from k equals 1 to p. Everything inside the summation is exactly what we want as a formula or an expression for x plus y all to the power of p plus 1. But we're starting too late and we're finishing too soon. We want to go from 0 to p plus 1. Now, and what do we do with these terms? Well, the awesome thing is now it's very simple. All we do is change the increment back to 0. Sorry, the index back to 0. And then now we're starting earlier again. And now we're going to have p plus 1 terms. And this effectively puts this back into here. Now, what's going to happen, this x to the power of p plus 1, okay, it's going to become p plus 1 minus k, which is just fine because k is 0, so it's still x to the p plus 1. Okay, this is where k equals 0. Okay, and then it's going to be y to the power of k, but k equals 0. So it's still the same term. Now, what's going on here? Well, we're going to have k down here, okay, but k is 0. So we can deal with the fact that the top is going to change in this binomial coefficient because p plus 1 to the power of, sorry, p plus 1 choose 0 equals p choose 0, as it equals anything choose 0, which it equals 1. All right. So just by changing this k index to 0, we've added a term to this summation, and the term that we've added is this term. So now we can remove it. We'll reintegrate this last term in the same way. We are going from k equals 0 to p. So we stop before we get to this term. It's as simple as changing that to p plus 1. Now, what happens to this term when we put it back in here? Now, let's keep in mind that this is x to the 0, y to the p plus 1. I mean, these are the numbers as far as we can write them with not knowing what p is, and it's p choose p. Now, when this goes in here, k has incremented all the way up to p plus 1. So when we have x to the p plus 1 minus k, we're actually having x to the p plus 1 minus p plus 1, which is x to the 0, which is what we want. And now k, it's gone all the way to p plus 1, so the k value is p plus 1. So y to the power of k is y to the power of p plus 1. So we're good. we're good here. Now, what goes on with this? Okay, well, something very similar, because when we've got p plus 1 choose k, so that's going to end up being the final coefficient. P plus 1 choose k goes to p plus 1, so it's going to be p plus 1. Okay, but what does that equal? Anything choose itself is going to be 1, which is the same as p plus, or p choose p. So that's okay. This is going to all evaluate to the same thing. So now we can get rid of that final term. And we are completed. We've completed the inductive step. So what have we done? We've shown the expression is true for x plus y to the power of 0. Okay, so what did we do with b? We've shown that if the expression is true for x plus y to some positive integer power, we are able to create the same expression for x plus y to the power of 1. Okay, now we've already demonstrated that it is true for some value p. I mean, we just set p to equal to 0. Since the expression is true for 0, it must be true for 0's successor, which is 1. And since it's true for 1, and it's true for 2, and since it's true for 2, it's true for 3, and so on, and so on, and so on. It spreads like dominoes falling over through the entire system of natural numbers. Let's review the inductive step with a specific example. Okay, we'll use x plus y to the power of 4, and we will derive that from x plus y times x plus y to the power of 3. Now, x plus y to the power of 3, we'll expand that, equals, now we're going to multiply this by x times y. So how are we going to do that? We're going to do it this way. Ta-da! And now this gets multiplied by x, being very informal here. So this 3, let's just change the color, becomes a 4. The 2 becomes a 3. We're incrementing every x term, and we get an x term here. Okay, now these are out of sync. Okay, the plot thickens because here's what we do with y. X stays the same, but now we increment y. Y to the power of 1, y squared, y to the power of 3, and y to the power of 4. Now, these seem like they're totally out of line. And let's amend that. And we do it by sliding over. Here we go. This looks more like what we had when we had the rectangles. And I'm going to move up, give ourselves some more space, finish this off. We don't need Pascal's rule to sum the coefficients here because now we're dealing with numbers. But do take note as we do this, the similarity to adding a new row to Pascal's triangle. And there we have it. This is x plus y all to the power of 4. And we constructed that as we did with the inductive step using x plus y times x plus y to the power of 3. And so, yeah, now you can have your chocolate. And as always, like, subscribe, comment, share. Thanks for watching.